Last class, we began talking about the preparation of materials from their raw state. We talked about particle size distribution. We talked about the importance of reducing the particle size in some instances. We hadn't talked about scaling it up, but we'll get to that later. We talked about the importance of getting the density in the green or unfired state as high as possible because that led to higher densities in the fired state. We talked about how do you go ahead and separate particles with different sizes with screening and meshes and some different techniques, as well as some classification or elutriation techniques. Elutriation, again, being great because they can be very high volumes or high amounts of materials that get separated, but the drawback is that you typically only get one separation step in each elutriation system. Right? There can be air classifiers where the air current blowing up these chambers carries small particles to one pathway, while heavier particles can resist the air current and gravity pulls them down. The same thing happening in the liquid system, but now it's centripetal forces pushing it one way while the fluid is flowing the smaller particles the other way. We talked about ball milling, that there's roller mills, that there's planetary mills, and that you have to select your media to get the right properties in your final product. That might be that you simply can't stand any impurities. If that's the case, you're going to want to pick a very tough, hard material that's less likely to break off and form impurities. If you can stand some impurities because you're going to remove them later, either magnetically, by dissolving them, or you just don't care about the impurities, then you can get away with other materials. One of the top-end materials is tungsten carbide, but it's going to be very, very expensive. A cup for a planetary mill can cost $5,000. Pretty expensive stuff, and the media is on top of that, of course. Right? I think we left off talking about media, and we didn't specify much more about the different types or the conditions. So let's talk about the conditions. You can do planetary milling, just like you can do sieving in either a dry state or a wet state. You can do your milling in a dry state or a wet state, right? And there's going to be pros and cons to each one. If you do milling in wet, meaning that has a solvent that your particles are sort of placed in, there are advantages that you're going to consume less power. You're going to have no dust, ideally. You can achieve high rotational speeds. You could then pair this with wet screening afterwards. And we know that wet screening is a little bit more efficient, assuming that you don't just clump back together again afterwards. You'll tend to get more homogeneous and smaller particles because you won't get things getting stuck, say, in the sides of the cup like that can happen in dry. And it's also compatible with later on spray drying and casting, both of which we'll be discussing soon. Now, if you do dry milling, you have other reactions or other pros and cons. One is that you avoid this problem of having to dry out your powder. If you dry it out, it's very likely that they're going to agglomerate together again. And if they agglomerate together again, that might have undone all the hard work that you put into it to separate them and reduce their size in the first place. You can also have avoidance of the reactions of powder with liquid. It might be that your liquid is completely inert with the material that you're milling, but it might be that it's going to react with it. What if it forms hydroxides? Is that beneficial or detrimental? It's something that you should be aware of. You generally can use less media, and there's less lining wear, right? So there's less media, which means there's going to be less media wear, and also less lining wear. You can start and stop at any time and sort of check on it. It's easy to optimize. Something I've left off here is also you can perform reactive ball milling. Right? And what that is you put in your two different materials and you start to mix them, and as you do so, they generate a lot of heat, right? So there's a couple different terms for this, but the principle is the same. You're letting the heat get so high that now you could actually have a reaction occurring inside your ball milling chamber. You could start out by putting magnesium and silicon metals inside, but as you ball mill it, you could be forming magnesium silicide, and this is actually done. So there's lots of reactive, or they'll call this mechanochemical, or reactive ball milling. Right? These are all terms that are talking about the same thing. Basically, you're doing your ball milling step, but you're letting it get so hot that the reaction is occurring in there, rather than a subsequent heat treating step. Right? The biggest problem with ball milling, for sure, if you dry mill, is particles sticking in the corners and then not getting milled up. Right? You can end up with other problems. Maybe you've got 2 or 3 different materials, and one is much more ductile and the other is much more brittle. And so they're going to wear and react at different rates, and some are going to get smaller than the others because like your ductile phase might just clump together in this milling process rather than break up into small pieces like you'd be liking. You can add some lubricant, which will improve flow and prevent moisture agglomerating. It doesn't need to be very much, but this can help things from sticking in the corners, adding just a little bit of lubricant. It can be a dry or a wet lubricant, I guess. Right? So what sort of distribution can we achieve after milling, right? And maybe pause for a moment and talk about these two questions. What should the distribution be after milling? And why should the powders be more reactive? Okay, another possibility is to do attrition milling. Attrition milling, if you remember before, our planetary and our roll mill relied on gravity to basically sling the media towards the other end of it where it's going to collide with the particle and break it up. Well, attrition milling goes a little bit further. In an attrition mill, you have a container, something about the size of a paint can. You can see it in this picture here. And all the media, it's totally filled with media, and your material would be soaked in here as well, right? And then it's got this rod which is going to rotate inside of there. As it does so, all the media is going to be vibrating around, shifting a little bit, right? So if you rotate this thing at relatively high speeds, or if you jerk it back and forth, you can achieve quite a bit of agitation, and there's a pretty high energy process to start breaking up particles. One thing that's nice about this is that you could have your media flowing in and out of this. Imagine for a moment you have your media flowing in here, right? Or not your media, your slurry, and then you have it flowing out over here, so you could be continually processing this if that was of interest. Or you could have another material flowing through there like a gas, right? Where that's going to ideally retain your media in here, but now you could have a controlled environment for, say, argon, or maybe you want an oxidizing or reducing atmosphere. You could control that because this is generally in a sealed atmosphere here, right? So that's attrition mills. There's vibratory milling. That's going to be a very similar process, but rather than this shaft rotating, it's just going to vibrate inside of there. And as it vibrates, it's going to cause the particles to, again, have contact with one another and break the particles up. There's fluid energy milling. Looking at this, it looks a little bit like the elutriation process. Essentially, you're going to be rotating this around in there. You're going to have your media inside with it. You're still relying on the kinetics of your media smashing into your particles, though. One thing that's nice, though, is that you can have an air current running through it. So just like elutriation before, you can be pushing out your small particles when they're done. So the large things will stay in there until they're broken down, but once they're small enough to be carried out, they can be carried out. You have a hammer mill. A hammer mill is a simple device. Larger rocks go in. This is rotating, and as it does so, these hammers crash against the wall and are able to break it up to smaller and smaller particles. Once they're small enough to fit through a sieve or a sizing in the bottom, they'll fall through. A roll crusher is basically the same concept. You take two rollers. They have a small aperture between these two rollers, right? Where you have one roller here, one roller there. A rock that big is going to have to get broken up as it goes through. So these are better for, I'd say, initial steps. Kennecott certainly has things like this when they're processing raw ore, but in the lab scale, we rarely need to use things like this because we order our powders from Sigma or Toso and whoever we're buying it from, and it's in a pretty close state to where we want it. All we need to do is some final sizing, generally in a planetary mill or an attrition mill, right? So those are the sort of start with the raw materials and go down in size approach. There's other ways to get the right size, and one of them is to make the compounds in the right size to start with. And so we'll call this chemical sizing, these series here. And the key feature of them is that we're going to be combining synthesis with getting the right size. We're going to do that in one step. And there's a couple different ways we can do this. One of them is to do precipitation. And when we talk about precipitation in this class, there's precipitation, there's co-precipitation, there's reverse co-precipitation. There's all these silly names, right? They're all talking about the same thing, though. In every case, you're going to start with something like a salt, right? So you could have, let's say, like aluminum nitrate, nonahydrate, right? So what you really want out of this might be just the aluminum, but you go ahead and add this whole compound because by adding this compound, this all separates out into solution from the aluminum, and you get aluminum 3 plus in solution, which is really nice because then you don't have to worry about breaking up an oxide where the oxide, the metal is going to be bound with the oxygen really tightly, and you have to overcome that with really a strong acid or something. This fixes all that. Most of these, they're water soluble. You drop it in a beaker of water and come back 5 minutes later and it's totally dissolved, which is really nice, right? So you start with salts and you dissolve them. We say salts plural because you generally do this with more than one compound. What if you're trying to make like an aluminum iron compound, for example? Well, then you'd start with the iron, right? Either 2 plus or 3 plus, right? You're going to start with the salt of that. You're going to get it in solution. And now the huge benefit of this approach is that these two ions, they're going to be right next to each other in solution. Or in other words, you don't have to rely on diffusion to move, if you had a particle, say of aluminum oxide and iron oxide. If this was a solid state synthesis, then you are relying on aluminum ions diffusing that way, iron ions diffusing that way, and getting mixture. Here we avoid that altogether. We get an intimate, we call it an intimate mixture of atoms, so they're mixed at the atomic scale simply because they're all dissolved in solution, and that's a huge benefit. So once they're in solution, what's the next step? Typically, you change the pH, temperature, or voltage, or sometimes all three. Generally speaking, most simple is just to change the pH. You change one of these things, though, and you cause whatever this mixture is here to be no longer soluble, and so it comes out as a solid. It goes liquid to solid. And as it comes out to a solid, hopefully your ions will still be mixed together in this intimate or atomic ratio where they're going to be mixed together very, very nicely, right? So how do we change the pH, temperature, or voltage and get the right phase that we're interested in? We use a pour-by diagram. A pour-by diagram is a tremendously useful diagram. Think of it like a phase diagram, right? A phase diagram, we typically are plotting against temperature and fraction between two components, say pure A and pure B. That's not quite what we have here. Here we're plotting pH and we're plotting volts, right? Applied voltage. But this, just as in a phase diagram, it tells you what phases are present, right? In this phase diagram, we know that this is alpha plus beta, this is liquid, that's alpha, beta, and so forth. We can do the same thing in a pour-by diagram. It tells us, hey, right here, iron 2 plus aqueous is the stable compound under these conditions. Meanwhile, if you change the pH to go up, iron hydroxide, which is a solid, right? Note the little solid sign there. That is what's stable. So you can use these pour-by diagrams to help you in your co-precipitation or your precipitation, right? You can simply change the pH down to low values at first, and you'll dissolve your material. So now you're going to have iron oxide in solution. Once they're mixed up or you've done whatever you want with them, you then move the pH back up by dripping this into a beaker that's highly basic. And every little drip, as it drops in there, all of the iron that was aqueous before is now going to have a thermodynamic driving force to switch back to a solid by forming a hydroxide. That solid would presumably be more dense than the solution. In general, it's almost always the case. And then you can separate it, right? You can filter it out or sieve it out, whatever you want to do with it. You can decant it, which means just pouring off the liquid from above. But this is a nice way to switch from the aqueous state, where it's nice and mixed together, to the solid state. So co-precipitation is just what I said before. You know, instead of relying on solid state reactions, which is relying on high temperatures and diffusion causing the ions to mix, you skip that altogether. In co-precipitation, they're already mixed together really, really well, which is awesome. So I want you to take and pause for just a moment here and talk about what would be the drawbacks. What would be the drawbacks to using co-precipitation as opposed to solid state diffusion? Particularly as you start changing the pH, what challenges might this result in? So go ahead and talk about it. Okay, hopefully you've talked about that and realized that one of the main challenges is that you must have a pH window that works. What do we mean by works? We mean liquid to solid for all ions, right? And so this is a problem. Things like silicon does not get dissolved at low pH unless you go to extreme conditions. Generally, it's easier to dissolve silicon at high pH. But things like iron, they have to be dissolved at low pH. And when you try and turn it into a solid, you have to go to high pH. So finding the right window where you can get all your species to sort of play nice and all go from liquid to solid at the same pH can be challenging. And if you mess up your pH, or if you don't control your pH very carefully, then you can miss it altogether, right? What if you've done all this effort to have these things come out and precipitate into tiny little nanoparticles, but then you don't control the pH and it goes a little bit too high or too low and it all dissolves again. You have to start back over, and that's a headache, right? What other drawbacks? Another thing is scale. You're typically generating a lot of waste, acid or base waste with this, so it's great for the lab, but it can be pretty rotten in terms of large-scale production because you might have a lot of waste that you're producing that might be even costlier or harmful to dispose of. All right, let's talk about another approach. This one's called freeze drying. Freeze drying is fantastic. For ceramics, it overcomes some of the main challenges associated with wet milling and wet sieving, which is getting rid of the liquid, right, without it clumping back together. Freeze drying fixes that step. And there's 4 steps, right? First step, you dissolve your ions in deionized water. So just like before with co-precipitation, you have to get them dissolved, right? Then step 2 is you rapidly freeze into droplets. 3, the liquid is removed via sublimation, right? Sublimation is what? Meaning that you never actually form a liquid. You go straight from the solid to the gas phase, right? That's sublimation. If it never becomes a liquid, then you shouldn't have a liquid region where ions tend to segregate or where you get agglomeration as the liquid sort of pulls in during the drying process. And then once you've done this and got it to a solid via sublimation, you then calcine, right? So you have to have ions that will go into solution first, and then you have to sublimate it. How do you do this? Well, if you are right here, if you have your material that's, say, we're going to change the temperature, right? So let's say you are right here in the water phase, right? If you go down in pressure, you're going to go from liquid to solid, right? But if you want to then get rid of that water phase and you heat it up, you're still going to have water right here, which is liquid, right? So what you want to do is go down below a certain pressure and then heat it up where it goes directly from, right? It's going to go from solid to gas, never forming a liquid. So you have to have a system that can pull a vacuum is basically what you have to have. You can do this at a variety of temperatures, but you have to have something that can pull a vacuum or you won't be able to get this happen. All right, there's something else called hot kerosene drying. Hot kerosene drying is pretty cool technique. You're going to disperse your salts in water or kerosene mixture, right? You're going to add an emulsifying agent. What does an emulsifying agent do? An emulsifying agent is something like oil plus water. If you have oil plus water and you take and you mix those two things up, you're going to have them separate, right? Where you'll have oil and water separate. But if you were to shake that up, then temporarily you'd have a bunch of small little particles which are separated from one another. You want to get it in that state, right? And then you're going to add this drip by drip into very hot kerosene, right? So you've got very hot kerosene, right? You're going to add this drop by drop into here, such that every single drop, when you drop it in there, it should have the opportunity to immediately evaporate the water, and you'll just have the solids precipitate. If your solids are completely soluble in the kerosene, this will not work. It requires that your materials be not soluble in kerosene, and it works for a lot of the ceramic materials that we are interested in. Okay, there's Sol-Gel method. Sol-Gel method's fantastic. You start with a stable dispersion, sometimes called a sol or a solution, right, of particles, right? You add some gel forming agent, something that will give it three-dimensional bonding. What do we mean by that? Well, if you've got your ion in solution, right, this is, say, some transition metal, and you've got another ion, transition metal over here, what you don't want is for these things to come together and clump. Right? You don't want clumping. So to avoid that, you have to put in something that's called a gel forming agent. So you put in polymers, right? You put in these polymers that stick to this and sort of hold these things separate from one another. What do you use? You can typically use citric acid. Citric acid is a good one, but there's certainly other ones, right? So you put your transition metals, or your metals, whatever your ions are, in solution. You add the gel forming agent, the citric acid. You start to remove some of the liquid. You evaporate it, right? Once you've removed all of your liquid, you're now going to have a really sticky tar-like substance at the bottom, and that's basically a citric acid transition metal ion mixture down there, the gel. And then you combust that. You just heat it up. Some people actually light them on fire directly. I have in the past typically just taken this whole crucible with the sticky tar-like substance at the bottom, and you fire it. And ideally, if you've done this correctly, as you fire it, all these ions that were held separately together will still be separate enough that you're going to have this intimate mixture, and you can get great ceramics forming. So this is a nice form of, it has some of the advantages of co-precipitation, but you avoid some of the problems of using the pH change to get it, right? And so this works really well for a lot of materials. You tend to get nanoparticles with really high surface areas, right? Okay, next let's talk about spray pyrolysis. I've got a postdoc in my lab right now who's an expert in this, and we're doing spray pyrolysis of iron sulfide for battery electrodes, right? How it works is you start out with a material that's in solution, right? You're going to send it down through a spray nozzle, which is going to have an atomizer. What does the atomizer do? It takes the solution and turns it into a bunch of droplets. It can be actually in the vapor phase entirely, or just very, very small droplets of the water, right? And then that goes and it gets directed onto some sort of heated surface typically, which has a substrate, and you're going to be putting down a very thin film on top of this heated substrate. The advantage to this is that this is basically glorified spray painting, right? This is like a highly controlled version of spray painting. You can put down pretty fast rates, and you can get very nice large areas deposited. However, the films that you put down aren't going to be as nice as some of the other techniques that are out there for putting down thin films. This sort of meets in the middle in terms of very low cost. There's no vacuum here, which is problematic in other things, but the film quality is not amazing, but it is flexible and high rate. Right? There's combustion. Combustion synthesis is when you put in compounds something like MgCO3, and you intentionally know that the CO3 that you're eventually at high temperatures, you're going to go to MgCO3, and you're going to combust it to form CO2 plus MgO, right? So this is going to burn off, but this is going to be a solid, right? And so you're going to be able to get rid of the agent that you're not interested in. So combustion synthesis, I'd find that typically using this is slightly better than the solid state. So if you had the choice of starting with magnesium oxide and aluminum oxide, or magnesium carbonate and aluminum oxalate or something, it's better to start with those, because as they burn off, as this bond breaks, as this thing has to break up and form new bonds, the likelihood of it being able to interact with the other species, say aluminum, is a little bit higher, and it's very easy to do. Hydrothermal. Hydrothermal is pretty interesting. You start out, it's hot pressurized water that causes the formation of very fine precipitates, right? So you typically take a vessel, right, and you screw this in. So this lid is screwed in, right? So that those are threads, and you put in here some amount of liquid, right? You might have H2O. You're going to add your transition metals or whatever your ions are of interest in with this thing, and then you're going to heat this up. And as it heats up, you're going to build up a really high partial pressure of oxygen, or of water in here. In fact, your total pressure, they call these bombs sometimes. You're going to generate really high pressures in here, which causes different phases to form, and you can generally tend to get some really fine precipitates forming in here. A lot of work has been done here. Something called Dark Reactions Project at Haverford College. Dark Reactions, Haverford. They do a lot of work on this, where they've shown basically all sorts of different mixtures that you put together. If you go here, it'll tell you whether or not what comes out is going to be forming single crystals or powders or lots of different things, right? So you can read more about it here. It's an interesting project, right? There's calcining. The thing to remember about calcining is to go from initial synthesis materials to correct phase, right? So for example, go from sol to phase of interest by combusting it, right? Or carbonates combust to correct phase. These would all be called the calcining phase, right? It's an initial heat treating step. It doesn't give you like a dense final product. It doesn't give you like a pellet or a disc or a cup or whatever you're making. It's still a powder when you bring it out, generally speaking, but hopefully it's now going to be the right phase. There's self-propagating synthesis. Self-propagating synthesis is something where you're going to add, where you're going to rely on A plus B forming AB, and this is going to be exothermic. Meaning it's going to have enough heat given off that this reaction self-propagates once you get it started. So a lot of times they'll take a system and they'll pass a huge current through, say, titanium, right? And this can combust, and as it does so, that serves as the initial exothermic reaction that then gets the rest of the reaction going. Professor Shetty has done this to make some tantalum carbides, some titanium carbides, so it's been explored for that. What's nice about it is that if you do this, you can put it in a very small vessel and you don't have to heat the whole vessel up. You just pass a current like a light bulb filament, right? A large amount of current through a very small material just to get it started, and then it'll self-propagate, right? Regardless of how you make your materials, right? We've described a whole bunch of different ways of making materials, and there's even more. There's certainly more, right? Once you make them, we now have what are called pre-consolidation steps. Consolidation is when you turn your powders and you pack them together and you're getting them ready to densify or sinter. Well, oftentimes before you do that, you still have some steps to do. For one thing, your powders might need to be, you might need to add some additives, right? Prior to shaping and densifying them. So what sort of additives are we talking about? Well, you can add binders. Binders is something, think of it like adding a little bit of honey to flour, right? If you tried to pack flour together, it's not going to stay together very well. But if you mix in a little bit of, say, honey or something, it might stick together really well. And anybody who's baked bread knows that there's sort of these binders that we add to things to get the right consistency of really dry, flour mixtures, right? Or maybe you want to add a lubricant, right? Instead of a binder. A lubricant might reduce die wall friction, right? You're going to put these in a die and you're going to press on it. And if the powders have lots of friction with the die wall, that is basically working against you packing these things together. It's going to prevent them from packing together well. You might need to add sintering aids during densification. These are things that will aid in the sintering process, which is when these particles now go from individual particles to a merged homogeneous body where you've gotten rid of the pores. We'll be talking about that in 2 chapters. You might have to add deflocculants, which are things that keep things from flocking together. So particles in solution, they might all clump together, which is called flocking. So you can add a deflocculant, which is something that will prevent that from happening. You can add plasticizers, something that will allow you to plastically flow the mixture, right? If you do something like injection molding, which is sort of like Play-Doh, right? If you squish the Play-Doh through the little shapes, it comes out with the shape that you squished it through. Well, it's only going to work if your material is significantly plastic, meaning you can flow it plastically a little bit, right? You might want wetting agents. So there's all sorts of things that you need to add to your powders way before you ever do your shape forming or consolidation steps. So how do we do that? Well, spray drying is one of the best ways to do that. Spray drying, you start out with your slurry, right? And this slurry here, that might be a mixture of your additives or it might be just the pure material. But the idea is that you spray it into here and you've got hot air blowing it that way. And so as this stuff sees the hot air, it's going to dry off, right? The solution, whatever this is in, whether it's water or some other solute or solvent, is going to dry off and you're going to be left behind with just the particle, right? So here you had your solution. After you dry that off, you got just your particle. So this is a really nice way to get just the right particle size you're interested in. For example, particle size reduction, ball milling, that might have reduced your particle size from something really big down to something really, really small. But then you might want something intermediate sized when you go to actually process this, and you want them all to be the nice exact same size. So this would be something like milling. Milling will reduce the size. But then, when you go through a spray drying process, it can get them all the exact right size, and you can have additives mixed in. As long as your additives, whatever they were, didn't combust during the spray drying process, because you typically do it above the what do you call it, the boiling point of water, because you want to get rid of the water, right? And as you change conditions of flow rates or rates at what you're spraying, all sorts of different conditions, you can actually achieve solid, hollow, collapsed spheres. You can make core shell particles, right? You can make all these interesting architectures of your particles, which is really useful. Okay, so next class, we're going to jump into shape forming, which is, all right, so if you want to make a fork or a spoon or a plate or a toilet, how are you actually going to make these oftentimes very complex shapes with ceramics? It's very challenging. Before we get to that, let's do an example problem with the time remaining. So the question I have for you is, I want you to make me this compound, gadolinium 8, calcium 2, SiO4, and there's 6 of those units, right? This is an apatite structure. Just like the hydroxyapatite that they use in your bone, this is a similar type of structure. This is not the ones that they use as artificial bone, but it's a similar type of structure. So if I wanted you to make this, I'm going to tell you, you go and look on the shelf, and in the shelf you find that you have 6 grams of gadolinium oxide, GD2O3. You've got 4 grams of calcium carbonate, and you have 20 milliliters of TEOS, tetraethyl orthosilicate, which is this formula, right? And it has a density given. So the question is, which one of these is the limiting reagent, right? Of these 3 different precursor reagents, we call these things, we call these reagents, meaning things that you start out with to have your reaction. Of these 3 reagents, which one is the limiting reagent? And the second question is, how many grams of the final product can you synthesize, right? And here's the molecular weight for these materials. So I'm going to have Josh walk you through this, but before we do that, because that'll be the last thing for this class, I want to show you a tool to use after you work through this with Josh. So Josh, don't have them use this tool yet. First, do it by hand, and then as a double check, we have this really, really great tool, right? ChemSolver. ChemSolver is fantastic. ChemSolver is a tool that my colleague at Johns Hopkins University, Tyrell McQueen, in the Tyrell McQueen lab, what it allows you to do is you can put in whatever you want to make. Like, let's say you want to make like titanium carbide, right? And you've got starting materials, titanium and carbon, right? Those are your starting materials, right? If you want to make, say, 1.2 kilograms, 1,200 grams, that's how much product you want. It'll tell you exactly how much of your starting materials to add in order to get that. So this is a really nice tool, and you can use it to double check that you guys got the right answer here. You just have to make sure that you put in this in the things that you ignore. It has a do not balance box, right? So let's say that you wanted to make now a different material. Let's say you wanted to make like titanium aluminide, right? But your starting material is titanium carbide, right? And aluminum. So you'd have to tell it, ignore carbon, right? Don't balance carbon. You want carbon to burn off, and then it'll do so, right? And it's going to modify these values. It says, hey, we're counting titanium carbide as just titanium, because we know the carbon's going to burn off, is basically what that's assuming, right? And that may or may not be a right assumption, but that's how this tool works. So if you start out with something, let's say we started out with calcium carbonate, CO3, and you were trying to form titanium calcium, right? If that's even a compound. This will work because all this CO3, it's going to call that CO3 just an oxygen. So this should work just fine, right? Okay, so in the remainder of the class, I want you guys to work through this and then double check that you know how to do that using this free ChemSolver tool.